Okay, class. So recall that in our last class, Monday's class, we were talking about discrete dynamical systems. And the example that we didn't quite finish dealt with spotted owl population in Willow Creek, California. And we had a stage matrix A. The stage matrix A is given by this matrix. And what that meant, if you recall, we talked about this. The stage matrix gives the chances well, there are three stages of this spotted owl: juvenile, subadult, and adult. And every entry has meaning. So like, for instance, the 0.30 here, well, that is going from juvenile to subadult. So a juvenile can become a subadult after a year with 30% probability, because 30% of juveniles survive each year to become subadults. However, can a juvenile become an adult after a year? Well, the answer is no. That is zero, right? Because juveniles first have to become subadults, and that takes a year, and then it takes another year to become an adult. So all of these entries have meaning. All of these entries have meaning. And what we did was, using the concepts in section 5.6, we found the eigenvalues and eigenvectors of that matrix A, and after k years, then the x sub k, which is the hold on here, one moment. Yeah, x sub k, which is the population of juveniles, subadults, and adults after k years. And I want to make sure I'm just saying everything right here. Or actually, it would be, let's see, one moment here. Yeah, x sub k, I want to rephrase that. X sub k here is the one moment. Just give me a moment, class. Yeah, x sub k is the number of juveniles, subadults, and adults after k years. Now, the units of this could be maybe in thousands or so forth, but yes, that's what that means. Now, if we found the eigenvalues and eigenvectors, okay, and we determined that the two terms can be ignored. This second term could be ignored because negative 0.03 plus 0.26i to the kth power, as k gets large, that term goes to zero. And then this term also could be ignored. So that over the long run, the evolution of the population for this owl species is determined by the first term. Okay, and we learned then, of course, the eigenvector that went with that first eigenvalue, okay, was this eigenvector, okay, and we determined that after k plus 1 years, okay, for k large, the number of or the population of juveniles, subadults, and adults after k year the population of juveniles, subadults, and adult owls in the k plus first year would be 1.01 times the population, those populations in the kth year. So that means there's a 1% yearly growth of the population. The owl species is going to survive. Okay, the owl species is going to survive. Well, and I understand, Belen, it's being recorded. Everything's being recorded. So, okay, so now this example here, if you look at MATLAB assignment number 4, okay, MATLAB assignment number 4, this example we're doing is the same as the case study example for MATLAB assignment number 4. So this will help you understand what this introductory example is talking about, and actually that will then help you understand how it'll give you insight on how to do, for instance, these questions at the end of MATLAB assignment number 4. And it's different, different populations of species, and there are actually 5 questions. Okay, so, all right, so let's continue this example here. Let's continue. So back we are here to the example we're talking about. And we're at this stage right here. Now, again, what we want to know, what we know that the population of spotted owls is going to grow, okay, for the future. It's going to grow for the future, and it's going to be a 1% yearly growth rate. But we also might want to know some other ideas. So, for instance, okay, let's make use of the eigenvector. We have an eigenvector here, okay? Here's the eigenvector. And that should have some meaning for us. We should be able to make use of that. So in the next page here, we note that as k goes to infinity, the population of owls between the juveniles, subadults, and adults will equal C1 times 1.01k times this eigenvector. But what we can do is we can rewrite the eigenvector so that we can better interpret what's going on between these between the juveniles, subadults, and adults of the owl species. So what you can do, for instance, is you can take the smallest number here, 0.0920, and factor it out. Okay, you can factor it out. So let me just see here. One moment, class. One moment. So go ahead and copy. Go ahead and copy. Go ahead and copy here. Okay, so there is an error here. There is an error. I was checking this. There's an error. This here, right here, should be 0. Man, I got to fix this font. Hold on here. Okay, let's try it again. Okay, so this should be 0.0920. That should be there. Okay. All right. So I had originally 1 over 0.0920. No, it should be 0.0920. And what I'm doing is I'm taking the smallest number in this eigenvector here, and I'm factoring it out. And then I'm just, you know, this eigenvector here is equal to 0.0920 times this eigenvector, that vector. And what I can do is, you notice I have a C1 in front of here. But if I define C2 to be C1 times 0.0920, then I have a C2 here. And all I'm doing is I'm rewriting the stage vector x sub k. Okay, and then what we can do is, you see, what I'd like to do is have for the 3 entries here, there are 3 entries in this eigenvector. Okay, I want those 3 entries to be basically as close as possible to integers, because I want to do an interpretation here. So what I'm going to do is I'm going to factor this. I'm going to factor out a third, and if I factor out a third, okay, then this vector here, what has entries 3.365, 1, and 10.2844. That's going to equal 1/3 times that vector there, with entries 10.09, 3, and 30.8. Fairly close to integers, okay? And now what I can do is I can divide C3. I can define C3 as 1/3 times C2. And then I'm able to write this. So now the x sub k vector is equal now to C3 times 1.01 to the kth power times the vector with entries 10.0904, 3, and 30.85. And you see, now we can say eventually, for every 31 adults, there will be about 10 juveniles and 3 subadults. And this gives you a lot of insight to this, how this population, how it works, so to speak. So in other words, why do you think? So there's okay, 10 juveniles. Okay, 10 juveniles. Okay, so like over the long run, if you look after many, and let me just see here, we're talking time here is in years. After, you know, over a significant period of years, if we were to take all these spotted owls, gather them up, we would see that the majority of the owls are the adults. Okay. And then the next amount, I want to say it the right way. 31, so for every 31 adults, there are going to be 10 juveniles and 3 subadults. So clearly there's more adults, right? Because the adults, when the owls after 2 years after a juvenile becomes an adult, the adult can hunt food better. It can, fight other owls for food. I mean, they in their territories. So if you make it to an adult, you have a better chance of surviving, right? Now the juveniles, there's a lot of juveniles because they're being fed by the adults, right? So the juveniles, they're going to hang around for a while, but look at the subadults. There's only the number of subadults. It's 3 subadults for every 10 juveniles and 31 adults. So that tells you that being a subadult, it's sort of a in terms of like the stages of the owl, juvenile, subadult, and adult. When the owl becomes a subadult, it's a little, well, why do you think it's less? Why do you think subadults, the number is less than the juveniles? I mean, in this population of owls, you're going to find fewer subadults than juveniles or adults. That's right, Cameron. The juveniles die off. Okay, juveniles get eaten by predators. They, maybe they fall out of trees. So it's risky being a juvenile, right? But so that's why subadults, there are overall less number of those. But once a subadult becomes an adult, they're gonna be around for a while. So you see, by rewriting this eigenvector in a different way, by just rewriting the vector x sub k in a different way, right? We can interpret what's going on in the population. That's what I'm trying to say. Does that make good sense? Are there any questions? Okay, Mikhail's comfortable. David's good, okay. Excellent, thank you, David. Thank you, Marcella. Okay, now another question we can ask is, yeah, and remember now, this interpretation that we're discussing down here, this interpretation is when k is large. It's as k goes to infinity. So this is the evolution of the species over time. Okay, so we could also ask, okay, well, what percent of the population eventually will be juveniles? What percent of the population will eventually be subadults? What percent of the population will eventually be adults? We can ask that question too, right? And actually, if we go to MATLAB assignment number 4 here, let me just go back to MATLAB assignment number 4. Let me bring it up here. Okay, so for the introductory example here, they say here, I know it's here, yeah, they say here, okay, hold on here. So this is, our matrix A, and, we found the eigenvectors, eigenvalues, and they're saying that 22, hold on here, I gotta keep, eventually 22.7% of owls in the population would be juveniles, 6.8% of owls in the population eventually would be subadults, and 70.5% of owls in the population would eventually be adults. So like 22.7% of the owls would be juveniles. So, where are they getting this? They just mention this, right? And they don't really show you how they're getting that. Now, I think you could figure out how they got that, but let me show you how they got that, okay? It all relates to the eigenvector. Okay, so if I now go ahead and clear this, okay, this here is an eigenvector of the matrix A. And even though what we did going, in this, to get this nice interpretation down here that relates the number of adults to juveniles and subadults, the eigenvector here, or this vector here, is just a multiple of the original eigenvector, right? And we can actually find the percentages of each class in what's called we call it the stable population, okay? Steady state population. So what if we did this? Let's look at the percentage of juveniles there will eventually be. You see, the first entry in the eigenvector is 0.3095. If I divide it by the sum of all the entries in the eigenvector, that's going to get me a percentage, 22.96%. That's the number of juveniles. Okay, and thank you, Yasin, I appreciate it. Thank you. The number of subadults, eventually, to get that, you're just going to take the entry for subadults, 0.0290, and divide by the sum of the entries. It doesn't matter that the entries are these, these numbers that MATLAB gave us. No matter what the entries are, the entries have to be in proportion. If you change the entries to different numbers, the entries still have to be in proportion to each other. So you see, by doing this, you can figure out everything you need. Eventually, there will be 6.83% subadults in the population, and eventually 70.21% adults in the population. Give you a moment to copy that. Okay, hold on here. I'm just looking at MATLAB assignment number 4. Yeah, this is called, what we're doing here when we find these percentages, we're finding the percentage of each class. Okay, we can call these different stages classes. We're finding the percentages of each class in the stable population. Okay, or the steady state population. Well, I don't want to necessarily call it steady state. Stable population, that's probably not the right word. The population is stable when you have 1% growth rate each year. Okay, then the population is stabilized. It's going to have that 1% growth each year. And then every year, these are the proportions of juveniles, subadults, and adults in that stable population. Right, steady state. That's right, Mikhail. That's right. I'm trying to be very careful with my with the words I use. Okay, because the population here, it never, the population here never, it's not, you don't have a stochastic matrix here, right? Where eventually the distribution stabilizes to like where the, well, you know what I'm trying to say. You don't have a matrix A, it's not a stochastic matrix. But in stable population, when the owl population has reached stable population, then at that moment you have 1% yearly growth rate, and these are proportions of juveniles, subadults, and adults. Are there any questions on that? You're all, Cameron says he can't hear me, but who you all can, okay, Mikhail can hear me, good, good. So this is going to be recorded. I'm going to put this recording along with MATLAB assignment number 4. Okay. So MATLAB assignment number 4 has 2 recordings to go with it. The one we did last class on this example, and this class, this recording. Are there any questions before I mean, basically now you have some good guidance for MATLAB assignment number 4. Who's feeling good? Give me a thumbs up if you're feeling all right. Wonderful. Mikhail's good. Marcella's good. David's good. Yasin's good. Excellent. Excellent. Okay. On that note, I'll stop the recording. Very good.